Hey guys, Miss Marusik here, and in this video we're going to talk about heating and cooling curves and how I can use these graphs to determine the heat change associated with a heating or cooling process. Now, before we get into the calculations, we're going to spend a little bit of time talking about the graphs. These graphs show what happens to the temperature of a substance as heat is applied or removed, depending on if we're moving up or down the graph, as well as transitions between the different states, so between a solid, liquid, and gas. Now, you notice the graph on our x-axis has heat. Depending on the design of the experiment, you could also have time here where it's assumed that if I'm applying a constant heat, if time is increasing, then the total heat that has been applied has increased as well. So again, depending on what kind of data you've recorded in the lab will depend on which of those two labels you use. Over here on our y-axis, you would have temperature. Now, no matter what kind of substance you have, these graphs will always have the same basic shape to them. You will always have a diagonal, then a plateau, then another diagonal, then another plateau, and then finally a diagonal. They always have that set basic shape to them. However, the temperature at which these plateaus occur at would be different for different substances. So let's talk about what each of these segments represents. And let's start over here with our first diagonal component. This would be what we have when heat is really low and our temperature is really low, and so therefore this would be representative of the solid state. And so what would happen is as I start to apply heat, I get more and more rotations and vibrational movement happening in my substance. And so slowly but surely that temperature is going to be increasing. I have an increase happening there of kinetic energy. However, at some point, I reach my melting point temperature. And when I reach that point, I'm ready to transition over to a liquid. But to do that, I need to weaken intermolecular forces. I don't totally break them here yet, but I definitely weaken them. And so to do that, you notice that I'm still applying heat, but I don't see any changes in temperature. There are no temperature changes during a phase change. And you're like, okay, well, if there's no temperature change, meaning no kinetic energy change, then where is this heat going that I'm applying? Well, what's happening is that I'm taking it in and applying that heat to changing my intermolecular forces. And so therefore I'm conducting potential energy changes at that point. And so that heat that I'm adding is going to potential energy change, not to changing temperature with kinetic energy. Now, when I'm along that plateau, technically, I am in a phase equilibrium between solid and liquid, but at some point I would eventually fully transition over to a liquid. And once I do that, once those forces have been weakened, then as I apply heat again, I will start to see my temperature increase again. So it would increase until I get to the boiling point temperature. Now, obviously, every substance has its own melting point and boiling point, which is why the placement of those plateaus is different when I'm talking about different substances. But at that boiling point, I again see another plateau. Now here, I'm totally breaking IMFs, and so that requires a little more energy change to occur there. But again, I see I'm applying heat, yet no temperature change is occurring because, again, the 3 P's of heating curves. The plateaus on the graph represent phase changes where potential energy is changing, not kinetic energy. Now, at some point, I would fully transition to a gas, and so then at that point, any heat changes would cause a kinetic energy increase. Now, depending on if I'm moving up or down this graph, will depend if my heat change overall is endothermic or exothermic. If I'm moving up this graph, then what I'm trying to do is overall break IMFs as I'm going from a solid to a liquid to a gas. And so therefore those processes would be endothermic and my delta H would be positive. If I'm moving down this graph, then I want to be removing heat because I'm forming IMFs. And so these would be exothermic, and they would release that energy, and so I would get a delta H value that was negative. Now, these are kind of hard to do the correct how does it feel, like if it feels hot or cold, because keep in mind that a lot of times if I'm, say, trying to break IMFs, I usually have it over some sort of heat source, like I have it over a Bunsen burner or a hot plate, and so the feel of it is impacted by that heat source itself. However, if you think about your body as providing the only heat source for a phase change, you will actually get the correct feel to that substance. Let me give you an example. When you think about sweat, the whole idea of why your body sweats is to cool it down. As the water evaporates from your skin, what that would do is that would break those IMFs. That takes energy to do that. So as the heat goes away from your body into that water to break IMFs, your body starts to feel cooler. And as we know, endothermic processes should feel cool to the touch. So again, if you're doing that more in a kind of a spontaneous fashion where your heat of your body is either being lost or gained versus heating it up on a heat source, you'll actually get the correct feel of that substance. Now, here's the issue with these sections. Each of these segments have to be calculated using a different formula. Now, let's talk about the diagonals for a minute. Obviously, on those, you have a temperature change that's occurring. And so when you have a temperature change, you're going to be allowed to use the MC delta T formula, or MCAT equation. That will work beautifully to calculate these segments. However, I will warn you, the specific heat of a solid substance is always different than the specific heat of that same substance as a liquid, which is different than the specific heat of it as a gas. And so each of these MCAT sections are going to need to be calculated individually with the correct specific heat. Now, the issue is with these plateaus is that I can't use MCAT at those sections. Why? I have no temperature change. And so if my temperature change is 0, it would look like my heat change overall is 0, which I know can't be. And so I'm going to need to use what's called the heat of fusion or the heat of vaporization to calculate these. Heat of fusion would be used along this first plateau. Heat of vaporization would be used along the second plateau. So we'll talk about both those values. So let's go ahead and look down here for just a moment at the steps to calculation. The first thing it says to do, if not given, sketch out a quick heating and cooling curve for the substance, indicating the melting and boiling points at the plateau. So I would draw myself an X and Y axis. I would draw a diagonal, a plateau, a diagonal, a plateau, and then a diagonal. And my two plateaus I would label with my melting points and boiling points. So that would enable me to figure out which segments I'm going through in the problem. So you see here, we would want to mark on the graph which sections are being discussed. Which sections am I going to need to do a calculation for? So then the issue is I've got to do a separate calculation for each segment. I would use MC delta T for any segments involving a temperature change. So again, those are your diagonals. Now, the convenient thing about the MCAT equation is that if you do your temperature change, final minus initial, your sign will come out correct here. These are not calorimeter problems, so you're not going to have to worry about system and surroundings and flipping the sign. You'll just be able to calculate your delta T and it'll come out appropriate for that substance. However, when I'm doing the plateaus, I cannot use that equation. I'm going to instead use fusion and vaporization heats for those segments. Heat of fusion is what we use when we are either melting or freezing, depending on the direction. And heat of vaporization would be when I'm doing my condensation or vaporization, so between a liquid and a gas. You notice here it does say we have to pick a sign. That's because they're going to give you these heats as an absolute value, and depending on if you're breaking or forming those forces will depend on if that sign is positive or negative. Now, one of the things we're going to have to watch out for with these are the units. And I say that because with MC delta T, a lot of times your calculation comes out in joules because the specific heat is in joules. But with heat of fusion and vaporization, a lot of times those are in kilojoules. These phase changes take quite a bit of energy, and so kilojoules is a more common unit to use. So you've got to be really careful on those units. And I say that because at the end, what you're going to do is you're going to add up the heat values for all the segments that you calculated. But when you do that, all the sections need to have the same sign. So that would be important when you're picking that sign on the plateaus. But all of the sections need to be in the same unit. I've got to either add all joules together or all kilojoules together. And so a lot of problems you get to decide what unit to report. You just want to make sure that your answer is consistent with whatever unit you're choosing to report in. All right, so with that said, let's go ahead and look at some examples of this on the next page. So it says here that below we have a heating curve for methane, CH4. And it's got some questions here that we want to answer about the graph. And so what I want you to do is I want you to pause the video and see if you can answer questions A through J. K is a calculation, and we'll talk about that part here in just a minute. But go ahead and pause it and see if you can answer parts A through J. All right, did you pause it? Did you try them out? I hope you did. Let's see how we did on these questions here. First thing it asked us is, what is the melting point of methane? And so that would be our first plateau here. And so that would be 90 Kelvin based on the scale that this particular temperature is in. The boiling point would be the second plateau. So that would be 110 Kelvin. It then asks which segments would involve changes in kinetic energy. Those would be our diagonal sections, so section P, R, and T. The potential energy segments would be our plateaus, the Q and the S, where we have those phase changes occurring because we're changing IMFs. So then it asks, in which segment would IMFs be the strongest, meaning a low potential energy? Well, strongest IMFs would be back here as a solid, and so that would be back here in section P. In the segment that IMFs would be the weakest, meaning a high potential energy, remember we have to have a high potential energy to hold those apart because they'd rather come together, that would be where those IMFs are the weakest as a gas, and so that would be segment T. I then asked in which segment would there be the most molecular movement. Well, hopefully we know that gas molecules move a lot faster and a lot crazier than solids do, and so therefore that would again be segment T because that's where my substance was a gas. All right, so now on question H, it asks why might segment Q be shorter than segment S? And it gave you a hint here. It said, hey, think about what you're trying to do to IMFs. Well, if I think about Q, I'm trying to go between a solid and a liquid there. So I'm trying to weaken IMFs, but I'm not totally breaking them yet. But in segment S, I am definitely breaking them at that point. And so you notice my heat of fusion is much smaller than my heat of vaporization. And that is very common in substances because when those IMFs totally break, that would need more energy to occur. Now, on part I, it says, hey, methanol has a heat of vaporization of 38.3 kilojoules per mole, which is higher than the methane one pictured of 8.2 kilojoules per mole. Why might this be the case? Well, if you think back to methane up here, it tells us that methane is CH4, so that carbon with the 4 hydrogens around it. That is super nonpolar. It's, a perfectly symmetrical molecule. And so therefore, that would only have London dispersion forces only. But methanol has that OH in it, which means we have hydrogen bonding IMFs that would be possible between those molecules. And so those stronger forces would require more energy to break. So your type of IMF can affect if something has a stronger or weaker attraction and therefore a higher or lower heat of fusion and or heat of vaporization. So then it says, notice the slope of segment P is greater than the slope of segment R. If you look back up here, P is kind of much more vertical, whereas R is a little more flattened out. And so it wants to know, why does P have that greater slope in comparison to R? Well, you really had to think about what that slope is showing. That slope is showing the temperature change that occurs as heat is being applied. So with segment P, because it has a greater slope, that means I'm getting more temperature change to occur, even though I'm adding heat at the same rate as I am with R. And so that would mean that I have a smaller specific heat value for segment P. I need less heat to go up by 1 degree Celsius. I can absorb just a little bit of heat and go up by 1 degree, and so I get those much faster temperature changes to occur there. So now, let's talk about the calculation together. It says here to determine the amount of heat needed to change 5 grams of methane gas from 120 Kelvin back to a liquid at 110 Kelvin. And it gives us a specific heat of methane gas. So the first thing I would do is determine my segments. Now, if for some reason they didn't give me my heating and cooling curve, the first thing I would do is to draw a sketch of this. Now, if they don't give you a sketch of this already, they should share with you the melting and boiling point, unless it's a substance that we already know the melting and boiling point of, like water. Hopefully we know that water is 0 degrees Celsius and 100 degrees Celsius for those variables. So once I know what that heating curve looks like, what I would then do is determine, okay, if I'm going from 120 Kelvin back to a liquid at 110, that would mean I'm going through this diagonal piece here from 120 down to 110, but then I'm also doing the phase change from the gas back to the liquid. And so because I'm going through 2 segments on that graph, I'm going to need to do 2 calculations. For segment 1, I would do an MCAT calculation because I have a temperature change there. On segment 2, I'm going to use this heat of vaporization because this is where I'm vaporizing and condensing depending on the direction I'm going. Now, something else to keep in mind, when I'm doing this, I am working backwards. So if I'm working back on this graph, if I'm going down the graph, then all of my heat changes should be negative because this is exothermic. If I was going up, then all of the heat changes should be positive and be endothermic. So pay careful attention to those signs as we're setting up our problems here. Okay, so let's go ahead and talk about the calculations involved for those 2 segments. So you notice as I did these, I labeled where my calculation was for segment 1 versus segment 2, so you could see how the different segments required a different formula to use. So on segment 1, where I was doing my diagonal component, I would want to use my MC delta T for that segment. Now, I don't have to worry about system and surroundings here because this is not a calorimeter problem. So I can simply just use the mass, the specific heat, and the change in temperature as given. I don't need to think about switching the sign or anything like that. In fact, if I do my temperature change correctly here, the sign actually comes out for us correctly. So with that said, my mass of my methane was 5 grams. It gave me the specific heat of methane gas, which matches up with the fact that I was in the 3rd diagonal, which is in the gas state. If you had a whole bunch of data to select from, you would want to make sure to pick the correct specific heat for that particular segment. So here that was 2.22 joules per gram Kelvin. You notice I rewrote it. Instead of using the negative exponents, I did divided by the grams in Kelvin in order to make that a little easier for me to understand. So then on my temperature change, as long as I do final minus initial here, this should come out correctly on the sign. So my final temperature for that segment was 110 minus the initial of 120, and that was in Kelvin. Now, keep in mind that if you had multiple diagonal sections you were going through, you would only want to put the temperature change here of that diagonal piece. So be very careful. You might have a larger temperature change overall, but you only want the temperature change of that segment when you're calculating it here. Now, that did get a negative 111, so it came out negative because of the temperature change, and it gave us joules here when I canceled out the gram and the Kelvin. So now I would calculate segment number 2. But when we're doing this segment, I no longer have a temperature change. Segment 2 was a phase change, and specifically it was the phase change between a liquid and a gas. And so therefore I would want to use the heat of vaporization for that segment, along with a little bit of stoich to convert. The issue is that the heat of vaporization is in terms of kilojoules per mole. Well, I don't have a mole value yet. I used 5 grams of the methane. So the first thing I would need to do is convert the grams into moles utilizing the molar mass of methane. So this is CH4's molar mass added together. Once I do that, then I can use the 8.2 kilojoules per 1 mole. However, you notice I did include a negative here because if I'm going from a gas back to a liquid, then that means that the IMFs are forming, and so therefore that should be exothermic, freeze to form. So I had to pick the sign on here. Now, my big hint is that all of your segments should have the same sign. So if this came out negative, then this other step should be negative as well. All of your steps should be negative because you're going down that graph. Now we do have to be careful here on unit. When grams and moles cancels, that actually leaves me with kilojoules. So when I get that answer, keep in mind that it has a different unit than the segment number 1 did. So when I go to add up these segments at the end to get the total heat change associated with that change that I made on the graph, I want to make sure all steps have the same unit and sign. So you notice I chose to do this in joules, so I left the negative 111 joules, and then I converted the 2.55 kilojoules into joules, but I left its negative there for that exothermic step. So then I just simply add those together, and that gets a negative 2,661 joules. Now, could you have left that in kilojoules? Sure, you could have converted this joules into 0.111 kilojoules and then added them up. And if you chose to do that, you would get a negative 2.661 kilojoules. Just make sure that whatever numerical answer you're reporting matches up with the unit that you're choosing to use, especially if they don't give you a unit to use in the problem. All right, I hope we're feeling good about heating and cooling curves, as well as performing a calculation involving those steps. Don't forget, each segment has to have its own calculation, and then at the end, you just simply add up all of those steps together. If you have any questions or need any help, please feel free to email me. Bye, guys.